Okay, welcome back Physics 30s to our next lesson in Unit A. This is 1.5 and today we're going to be looking at elastic collisions. So let's consider that we have these two marbles. I realize you see a bullet in the middle of your screen. That's just the background. That actually has no effect on this example. So let's just imagine those two marbles, and the first one, the blue one there, is going at 2 meters per second and the green one is going at -4 meters per second. The blue marble is a bit bigger, it's 150 grams, and the green marble is 60 grams. So if we're looking at the momentum of this, like we did in the last lesson, the momentum of the blue marble is 0.30 Newton seconds. That's the momentum of the first one, and of the next marble is -0.24. So our starting momentum total would be 0.06, right? The sum of those two numbers. So they're going to come together, bounce off each other, and then move in opposite directions for this case. At the end, the blue marble is going at -1 meter per second, and the green marble is going at a positive 3.5 meters per second. So they flip directions. So now, based off of their masses, this is the final momentum of the blue marble. It's -0.15, and the green marble is 0.21. Then we look at the final momentum, and it's the exact same as the start. This was the focus of last lesson in saying that if there was no external forces, momentum would be conserved in a collision. So that's a bit of review from what we looked at from last lesson, and today's lesson is going to be pretty similar, looking at doing those calculations, but then also considering energy. So let's take a look at energy in this example. I'm going to remove all the momentum stuff. Now I just see that we have a 150 gram mass going at 2 meters per second at the start, -1.0 meters per second at the end, and a 60 gram mass going at -4 at the start and positive 3.5 at the end. Let's look at the energy now. If I'm going to calculate half mv squared, like we saw before for kinetic energy, for the initial energy of the blue marble, it would be 0.3 joules, half mv squared. And I look at the starting energy of the green marble, and it would be a 0.48 joules. Now it's important to remember here that energy is a scalar. It doesn't matter on the direction. An object has energy whether you throw it that way or you throw it this way. It still has that certain amount of energy and ability to do work on another object that is the same. So the energy of these is going to be both positive, and we're going to add them together to get the initial energy. So then my initial energy is 0.78 joules. Okay, let's take a look at the end. We have -0.1 meters per second times by its mass. Again, energy is scalar, so it has a positive value of 0.075 joules. And at the end, the green marble is 0.365 or 3675 joules. We add those together and we get 0.4425. In this example, we see that although momentum is conserved in the collision, energy is not. Well, how can that be? We said that there was no external forces. Well, what happens is when those marbles smash together, they also lose a lot of energy to heating up those objects themselves. This isn't friction to an external source, but there is heating up of those two marbles. There's also probably kind of a loud smack or crack that you're going to have some energy going away to sound as well. So on this slide, we can see that when the marbles come together and when they make contact, there's going to be some energy lost to sound. There's also a significant amount of heat that is going to be created in there. It's very quick how it heats up and then dissipates that energy, but if you took two steel balls and smacked them on a sheet of paper, you'd actually get a burn mark on that paper because just for that moment and in a very small area, there is a large amount of heat produced when we have a collision. So if I consider the numbers here and I subtract 0.3375 joules, that must be the energy that was lost to heat and to sound. Then the remaining 0.4425 joules was in the kinetic energy of the two marbles. So we haven't gotten rid of energy, but for those two objects, it was not conserved. So that's the focus for this lesson, looking at energy and momentum and seeing if they're conserved in collisions. So we call these collisions either elastic or inelastic. An elastic collision is when momentum and energy are both conserved during the collision. An inelastic collision is where momentum is still conserved in the collision, but energy is not. And that's like the example we just saw with the marbles. Now, for momentum to be conserved in both of these, we are assuming that there are no external forces. That would change the conservation of momentum. But again, like we said in last lesson, we're going to be considering situations where that would be negligible compared to the amount of force applied on each object by the other object. So that's the concept, and we're going to jump straight into an example here. It's kind of a complicated example, so we're going to take our time with it. It says a bullet is fired into a block of dense foam. The bullet is 10 grams, and the foam block is 3 kilograms. The foam block is hung from the roof by a 1.5 meter string, and the foam and the bullet, when the bullet hits the foam, it swings up and makes a 45-degree angle. What was the initial speed of the bullet? So a little animation here, the bullet fires into the foam and the bullet swing up like this to make a 45-degree angle. We want to figure out the initial speed of the bullet. So I've minimized the information up there, and now you can see why the background was a bullet. This is kind of the focus of this lesson, was this example. And we're going to do two things. We're going to find the initial speed of the bullet, and then we're also going to see if this was an elastic or inelastic collision. So what I'm going to start here with is looking at the conservation of momentum, because we know that has to be conserved considering there's no external forces and there hasn't mentioned that there are any. So I'm going to start with Pi is equal to Pf. It's a good way to start any conservation of momentum question. Now at the beginning we have the bullet, so I'm going to put the momentum of the bullet at the start plus the momentum of the foam at the start. And that's what I have as two separate objects at the beginning. At the end, I have them together. This would be a hit and stick collision from the last lesson. So I have the momentum of the bullet plus the foam together at the end. Okay, that's our setup here, because we go from two separate objects to one together. The bullet definitely has momentum at the start, so I'm going to put mv plus the momentum of the foam at the start is just sitting there stationary. So that actually is just 0. And at the end, I'm going to have the mass of the bullet plus the mass of the foam multiplied by the velocity. So if I plug in the values I know it's a 10 grams, so that'd be 0.01 kilogram bullet, and I don't know the velocity, is equal to the 0.01 kilogram bullet plus the 3.0 kilogram foam, so let's just make that 3.01, times by the velocity of the foam and block together. This seems a little bit challenging because we're trying to solve for this velocity here, but we don't have this velocity over here. Situations like this often come up in Physics 30. It looks like a normal question with momentum, but we're lacking some information. So what we have to do is figure, is there anything else I know about physics that get me to solve or provide that value for velocity? And in this case, there is. We know some things previously about energy. When we have a pendulum that is going fast, swings up to a position where it stops, that's a conversion between kinetic and potential energy. And we have formulas for calculating this. And before I get into that, you might be thinking, well, I don't know if energy is conserved. Note that this part, when the bullet is already in the foam and it swings up, is not a collision. That is just a transfer of kinetic energy to potential energy. And so we're not worried about if this is elastic or inelastic for the swing part. We'll find out later if when the bullet goes into the foam, if that was elastic or inelastic. But once it is in the foam and moving, it is not a collision, it's just a swing of the pendulum. So we should be able to use conservation of energy for this part. So I'm going to write just below here that the energy initial is equal to the energy final. And again, this is talking about the swing. So we start with half mv squared, that's the bullet and the block moving quickly, and then mgh when they swing up to their height where they stop, mgh. This is good that I have a velocity term. I can figure out the speed that it was moving at the start, which is what I'm looking for right here. So to solve this, I can cancel out mass because that's on both sides. And then I just need to times by 2, so 2gh, and then take the square root to get velocity on its own. So if I can plug in 2 times g, 9.81, times the height. But we don't have the height. Okay, so now we have a similar case. I don't have information, but is there anything I know about physics that I could use to solve it? And we do know about angles and trigonometry to figure out the height difference. So what we have to do here is look at that angle of 45 and draw a triangle like this. I'll make it a little bigger down here. We know that this angle is 45 degrees, and we know that the length of the rope is 1.5 meters. And that may seem like I still can't tell what's going on down here. except for that the length of the string stays the same the whole time. So this length of the string I'm putting up at the top here with orange, all right, has to be the same as this amount. So if I can figure out this section, I'll highlight it on the big diagram as well, this section of the triangle, and find the difference between that and the length of the rope, I can figure out how much higher this value right here that the block swung up. So first I have to find this side that I have in orange. So we're going to use cos 45 degrees times by that 1.5, and I get a value of 1.0607. And that's right, oh, there's the triangle gone. That is right here. So saying that compared to the full length of 1.5 meters, the difference between that, I'm gonna put in red over here, if we're looking in this place, is this part is the height that it raised up, and this part is what I just calculated as 1.0607. So let's take 1.5 meters minus the 1.0607 to find the amount that it raised up, and I'm getting a number of 0.4393 meters. That's the height that it raised up once it swung. And now I can use that in my conservation of energy calculation. So it's going to go down in there for height. So 2 times 9.81 times that 0.4393. Make sure you take the square root and you get an answer of 2.9360 meters per second. So that's how fast the bullet and the foam block are moving at the start of their swing. So that's right after the collision, how fast they're going. And we can plug that number back into here now. And we're pretty much ready to finish this off. So we can take the 3.01 multiplied by that velocity, and I'm getting a number of 8.8372, keeping lots of digits, Newton seconds for our final momentum. So that should equal our initial momentum, which again was 0.01 kilograms times by the velocity of the bullet. Let's just divide by the 0.01 on both sides, and we get a number for the velocity. Sorry, this looks a little bit messy now. Velocity is equal to our rounded number to 2 digits. Actually, let's start with the unrounded, 883.7. We need to round to just 2 digits because there's the 1.5 meter spring there. Meant to give 3, but that's all right. We'll round this to 8.8 times 10 to the 2 meters per second. And that is the velocity of the bullet. So fairly challenging question. First started the way that we normally solve conservation momentum, then you had to use energy, then you had to use trigonometry. But these were all skills that you had, it's just combining them to solve a problem. And that's the kind of things that we're looking for in Physics 30. And now the last part of the example, which was actually the focus for today, is looking at if this is an elastic or inelastic collision. So comparing the energy of the bullet at the start compared to the energy of the bullet and the foam right after the collision. So I'm going to write this as our energy at the start is just of the bullet, so half mv squared. And we calculated the velocity there. So I'm going to put half times 0.01 kilograms times the velocity of 883.7 squared. Let's see what we get with that. I'm getting a big number of 3,904 approximately joules of kinetic energy at the start in the bullet. Now let's consider the foam and the bullet at the end. That's again kinetic energy right after the collision. So we go half mv squared afterwards. That's 0.5 times our 3.01 kilograms, so significantly more mass, but the velocity is significantly slower. We had that value from before being 2.9360, and that's squared. And there I'm getting a mere 12.97 joules. So we started with way more energy when the bullet was fired compared to the block and the bullet at the end. This has to do with the square part and the velocity. We began with a small mass with the bullet with a high velocity. Because it's squared, it's that mass times velocity twice. So that velocity has a big impact on our kinetic energy. In the next part where we had the block and the bullet, it was a higher mass, so that mass was bigger, but it was times v twice, and the v was much smaller. So that's the reason that the energy conversion isn't the same as the momentum conversion. And in this case, we can see it's not conserved, so it'd be inelastic for a collision. Where'd that energy go? There could have been some loss to sound, some of heat of the bullet and of the foam block. So thank you very much for watching this video. I hope it helped with your calculations for elastic and inelastic collisions. Give those practice questions a try, and I will see you in the next video.